You know what's strange? Right now, you're experiencing something so basic you've never even questioned it. Your body resists when you try to move it. Push yourself away from your desk. Feel that pushback. That's inertia. But here's the thing that should keep you up at night. Why? Not because of gravity. That's different. I'm asking why you have mass in the first place. Why does your body resist acceleration? Why does a truck fight back harder than a bicycle when you push them? And here's where it gets weird. Light doesn't have this problem. Light has no mass at all. It zips through the universe at the maximum speed anything can go, completely unburdened. So why do you have to drag all this mass around? For thousands of years, nobody even thought to ask. Mass was just there, like color, like shape, end of story. But that answer, it's about to fall apart. Let me tell you something that sounds impossible. Empty space isn't empty. I don't mean there's dust floating around. I mean if you took a box, removed every atom, every particle, every last photon of light, you still wouldn't have nothing. You'd have a very busy place. Space itself has properties. It can bend, it can vibrate, it can store enormous amounts of energy. Modern physics discovered something wild. All of space is filled with invisible fields, not things you can touch, but conditions, properties that have values everywhere. Think about temperature for a second. Temperature isn't an object. It's a property that has a value at every point in your room. You don't ask, where is the temperature particle? You ask, what's the temperature here? Fields work the same way. There's an electric field everywhere, a magnetic field everywhere, and several other fields you've never heard of, all stacked on top of each other, filling every cubic centimeter of the universe. Now here's the kicker. What we call particles aren't actually tiny solid beads bouncing around. They're ripples in these fields, vibrations like waves on the surface of a lake, except the lake fills all of reality. An electron, that's a ripple in the electron field. Light, a ripple in the electromagnetic field. At the most fundamental level, everything reduces to patterns of vibration in invisible fields. But this creates a problem, a really big problem. By the mid-20th century, physicists had beautiful equations describing how nature worked at its deepest level. There was just one catastrophic issue. The math that described fundamental forces worked perfectly, but only when certain particles had no mass, particularly the carriers of those forces. The equations were elegant, symmetric, consistent, but only for massless particles. The moment you tried to give these particles mass in the obvious way, the whole mathematical structure collapsed into nonsense. But look around. You exist. Tables exist. We're clearly not living in a universe of pure massless particles. Something had to give. Light gave us the first clue. Light has energy. It can push things, heat things, carry momentum across the universe. But it has no mass. No matter how much energy you pack into a beam of light, it always moves at the same speed, always. Electrons, on the other hand, do have mass. Push an electron and it resists. It behaves sluggishly compared to light. Both are field vibrations. Both are governed by similar equations. So why does one act heavy and the other act weightless? This question haunted an entire generation of physicists. The answer, when it finally came, was so unexpected it changed how we understand reality itself. This is where it gets beautiful. Physics has an obsession with symmetry, not because physicists are artists, though some are, but because symmetry is power. When you demand that the laws of nature look the same everywhere, at all times, under all conditions, you eliminate countless possibilities. You narrow down what the universe is allowed to do. But here's the catch. Sometimes reality doesn't want to live in the most symmetric state. Picture a pencil balanced perfectly on its tip. That setup is completely symmetric. Every direction looks the same. But the pencil never actually stays there, it falls. And when it falls, it picks one direction. The laws still allow all directions equally, but the outcome doesn't. This is called spontaneous symmetry breaking, and it's everywhere in nature. Ice crystals choose particular angles, even though space itself has no preferred direction. Magnets align their atoms in one way. Even though the fundamental forces treat all directions the same, the laws can be perfectly symmetric, even when reality is not. Hold on, this changes everything. Imagine a landscape covered in hills and valleys. Drop a ball on top of a hill, and it's in a symmetric position. It could roll in any direction, but give it the tiniest nudge, and it rolls down into a valley. Once there, the symmetry is broken. Fields have landscapes too. They have energy, and that energy depends on the field's value. Here's a crucial principle. When systems can exchange energy with their surroundings, they tend to settle into the lowest available energy state. Not because nature is lazy, but because that's simply the most probable configuration. For most fields, the lowest energy is zero. The field just isn't there. But not all fields play by these rules. Some fields have an energy landscape where the lowest point, the most stable, calm configuration, is not at zero, it's at some other value. And here's the crucial part. That field sits at this non-zero value everywhere, always. Throughout all of space, you're immersed in it right now, not in the sense of swimming through it, but in the sense that it exists at every point in space, including the space you occupy. This field fills your room. It filled the space between stars before those stars were born. It permeates the gaps between the atoms in your body. You can't turn it off. You can't escape it. And some particles, not all, but some, interact with this field as they move through it. Picture walking through an empty room versus walking through a crowd. In an empty room, you glide straight across. But in a packed crowd, you have to push through people. They slow you down. From a distance, it looks like you've gotten heavier. Nothing has been added to you. You haven't gained any stuff. The difference comes entirely from your interaction with the environment. The Higgs mechanism works on a similar principle, though the details involve quantum field interactions, rather than literally pushing through a crowd. Now, you might be uncomfortable with that. You might want mass to be something more concrete, more real. But here's what physics teaches you. The things that feel most solid and real to you, the table you're sitting at, the ground under your feet, are built from interactions and relationships, not from stuff in the way you imagine it. When certain particles move through this field, they interact with it, they drag against it, they struggle. That struggle is what we experience as mass. Electrons interact strongly with the field, so they're heavy, well, heavy for subatomic particles. Quarks, the building blocks of protons and neutrons, interact even more strongly, they're heavier still. Photons, particles of light, don't interact with this field at all. They pass through it like it isn't even there. That's why light has no mass. That's why it moves at the cosmic speed limit. Mass isn't a substance. It's not stored inside particles like coins in a pocket. Mass is a relationship. It's what happens when a particle tries to move through a field that pervades all of space. This solved the crisis in physics. The equations could stay symmetric and beautiful. The fields could behave elegantly. And yet particles could still end up with mass, not because mass was built into them from the start, but because the universe itself isn't empty. But here's where it gets testable. Every field can vibrate. A calm lake has a surface. Throw a stone and you get ripples. Those ripples aren't separate objects. They're patterns in the water. But they move, they spread, they interact. They behave like things. If space is filled with a field sitting in its lowest energy state, then that field can be disturbed. It can ripple. And every ripple in a field shows up as a particle. This is a hard prediction. If the field exists, its vibration has to exist too, not because physicists wanted it to, but because the math leaves no room for anything else. But there's a problem. Making this field vibrate takes an absurd amount of energy. Think of it this way. Some valleys are gentle. A light breeze can create ripples on a pond, but other valleys are steep, carved deep into bedrock. You need an earthquake to shake those. The field we're talking about sits in an incredibly steep valley. Creating a ripple requires concentrating more energy in one spot than exists in most natural processes, most of the time. The universe doesn't bother. The field just sits there, quietly doing its job, giving mass to particles that interact with it. But if you could concentrate enough energy, if you could slam particles together hard enough, fast enough, you could briefly knock the field out of its calm state. You could make it ring like a bell, and that vibration would appear as a particle, a very heavy, very unstable particle. That would exist for less than a trillionth of a second before decaying into other things. So the question became, how do you ring a bell that fills all of space? You build the largest, most precise machine in human history. Deep beneath the border between France and Switzerland, there's a ring. 27 kilometers around. Inside that ring, beams of protons race in opposite directions at 99.9999% the speed of light. Superconducting magnets, colder than outer space, keep them on track. And at specific points, those beams cross, they collide, not gently. These aren't fender benders. These are head-on crashes at energies that haven't existed naturally since microseconds after the Big Bang. When protons collide at these speeds, their energy doesn't just disappear. Energy can't be created or destroyed, but it can change form. And for a fleeting instant, that energy can reorganize into particles that are far heavier than the protons themselves. This isn't magic, it's bookkeeping. Nature keeps meticulous accounts, but it allows the currency to change. Most collisions produce ordinary particles, quarks, electrons, photons, background noise. But every once in a while, maybe one collision in 10 billion, something different happens. The field that fills all of space gets hit hard enough to vibrate. And that vibration appears. Here's the catch. The particle doesn't live long enough to leave a trail. Its average lifetime is roughly 10 to the negative 22 seconds. That's a decimal point, followed by 21 zeros, and then a 1. In that impossible sliver of time, it decays, it transforms into other particles that do leave trails. Electrons flying off in one direction, photons in another, specific patterns, specific energies. What physicists actually see isn't the vibration itself, they see the aftermath. Imagine trying to prove that a specific type of firework exists, but it explodes the instant it's created. You'd have to look at thousands of explosions, measure the fragments, and search for a pattern that appears more often than random chance predicts. That's what they did. Billions of collisions, trillions of particles, petabytes of data analyzed by algorithms looking for the tiniest statistical excess, a bump in the data where there should be smooth background. This is where people misunderstand discovery. There was no eureka moment. No one looked at a screen and shouted, "There it is." Science doesn't work that way. Discovery is slow. It's an excess here, a consistency there. It's multiple detectors seeing the same pattern. It's checking and rechecking, eliminating alternative explanations one by one, until you're left with something you can't explain away. When the evidence finally became undeniable, what was celebrated wasn't just a particle. It was confirmation of an entire picture. A picture where fields fill space, symmetries guide the laws, and mass emerges from interaction, rather than existing as some fundamental stuff. Let me be clear about something. Most of the mass in your body doesn't come directly from this field. Surprised? You shouldn't be. Protons and neutrons, the particles that make up atomic nuclei, are made of quarks. Those quarks do get their mass from the Higgs field, but most of a proton's mass, about 99% of it, comes from the binding energy of the strong force holding those quarks together, and from their kinetic energy as they zip around inside. So while the Higgs field gives fundamental particles like quarks and electrons their mass, the bulk of ordinary matter's mass comes from a different source. The energy locked up in the strong nuclear force. Wait, you might be thinking, then why does everyone make such a big deal about it? Because it solves a specific, crucial problem. Without this field, electrons would have no mass. Without mass, electrons would move at the speed of light like photons do, and they couldn't settle into the stable quantum states around atomic nuclei that make chemistry possible. No stable atoms. There'd be no chemistry, no molecules, no you. The field may contribute a small percentage of mass by weight, but it's 100% responsible for the possibility of matter being stable enough to form complex structures. It's the difference between a universe of pure radiation and a universe where galaxies, stars, planets, and people can exist. That's worth celebrating, but it's also worth being honest about. This isn't the God particle some headlines called it. It's not the source of all mass. It's not the answer to every question in physics. It's a piece, an essential piece, but still just a piece of something much larger that we're still trying to understand. If you came here looking for a final answer, a complete, tidy explanation of reality, I have bad news. Physics doesn't work that way. Every answer opens new questions. Why does this field have the particular strength it does? If it were just slightly different, atoms might not exist. Chemistry would fail. Stars might never ignite. Why is it tuned to allow a universe where complexity can emerge? Why do different particles interact with the field so differently? Electrons get one mass, quarks get different masses. Photons ignore it entirely. We can measure these differences. We can encode them in our equations. But we don't know why. And then there's the really troubling stuff. Gravity doesn't fit into this framework at all. The equations that describe gravity and the equations that describe this field-based picture of particles are fundamentally incompatible. We use both because they each work in their own domain, but we know that's not a complete answer. Most of the universe is made of something that doesn't interact with light or the Higgs field, at least not in any way we've detected. We call it dark matter because we literally can't see it. It has mass, so it bends space and holds galaxies together, but beyond that gravitational effect. We don't know what fields it might interact with, and on top of all that, the universe is expanding, accelerating, driven by something we call dark energy. That we understand even less than dark matter. So no, we haven't figured everything out. We've figured out one mechanism, one beautiful, testable, confirmed mechanism that explains part of how the universe works. The rest, still a mystery. So what should you take from all this? Not the name of a particle, not the details of detectors or equations. Take this. The next time you push against a table and feel it push back, recognize that you're not just dealing with solid stuff, you're experiencing a field that fills all of space in its lowest energy state. You're feeling the resistance that emerges when particles try to move through that field. You're interacting with the same mechanism that allows atoms to exist, chemistry to work, and stars to burn. Mass isn't a thing you have. It's a relationship between you and the structure of empty space. When you lift something heavy, you're not just overcoming inertia. You're fighting against every particle's interaction with a field that pervades the entire universe. The universe is far stranger than it appears. Space isn't empty. Particles aren't solid. Mass isn't stuff. Everything you've been taught to think of as permanent and real is actually fluid, dynamic, emerging from interactions and relationships. And we know this not from philosophy or guesswork, but from experiments, from predictions tested against reality, from mathematics that describes what we see with sometimes absurd precision. Physics doesn't give you comfort. It doesn't give you certainty. It doesn't promise that we'll figure everything out tomorrow or even in your lifetime, but it gives you something better. It gives you reality, not the reality you want or expect, but the reality that's actually there, waiting to be discovered. The universe is subtle. It doesn't arrange itself to make sense to you. It simply behaves according to laws that are indifferent to human preference. But here's the remarkable thing. Those laws can be understood, not all at once, not without effort, but piece by piece. Through careful observation, clever experiments, and rigorous thinking, we can figure out how it all works. We've done it before. We'll do it again. And the field that gives you mass, that's just one chapter in a much longer story, a story that's still being written, one discovery at a time. The next time someone tells you empty space is empty, you'll know better.